This is the 6.05 mole volume relationships recording. A relationship exists between the volume of a gas and the number of moles of the gas. In the laboratory, chemists often have to measure the amounts of reactants in products. Many times, one or more of the reactants are gases. Measuring the mass of atoms in a gas can be difficult. Measuring volume is quite easy. The volume of a gas depends upon temperature and pressure and is related to the number of molecules present. In this lesson, you will learn to interconvert between volume and moles. Goals for this lesson: explain what is meant by standard temperature and pressure, which is abbreviated STP of a gas, and my car and automobile people, STP like the oil, but this time meaning standard temperature and pressure. Define molar volume of a gas, discuss Avogadro's hypothesis, solve mole volume problems. Mole to volume relation, derived from these equal measurements. 1 mole of gas is exactly the same as 22.4 liters is exactly the same as 6.022 times 10 to the 23rd gas molecules, if the gas is at standard temperature and pressure. Again, there's a student guide you can use. Chemical reactions often involve gases. Many chemical reactions involve gases. For example, in the Haber process, gaseous nitrogen and gaseous hydrogen are combined at high temperature and pressure to form gaseous ammonia. Likewise, water is formed when hydrogen gas and oxygen gas combine. Finally, when sodium metal is exposed to chlorine gas, sodium chloride, or the table salt that you eat, is formed. For reactants and products that are solids and liquids, chemists can easily measure the mass. Like you just put it on a balance. However, measuring the mass of a gas is not as easy. Instead, chemists measure the volume of a gas, so how much space it takes up. When doing stoichiometric calculations, chemists convert volumes of gases, which are measured in liters and milliliters, to moles. In this lesson, you will learn how to do these conversions. First, though, look at the behaviors of gases. Volumes occupied by gases depend on temperature and pressure. A gas has no definite size or shape. It expands to fill its container. Consider a balloon filled with a fixed amount of gas. The gas molecules are constantly moving and bombarding the inside of the balloon, thereby exerting an internal pressure and pushing the balloon outward. The internal pressure increases as the temperature increases. As a result, the balloon expands as the temperature increases, it contracts as the temperature decreases. So if you've ever bought like a helium balloon in winter, when you take it out in the car, it shrinks, and then when you bring it back in the house, it expands. Meanwhile, the atmosphere exerts an external pressure that pushes in on the balloon. As atmospheric pressure increases, the volume of the balloon decreases and vice versa. Atmospheric pressure is also related to temperature. The balloon's final volume is reached when the internal pressure from the gas equals the external atmospheric pressure. The balloon's volume, the gas's volume, then depends on the temperature and atmospheric pressure. All right, so let's talk a little bit about what atmospheric pressure is. Atmospheric pressure is the fact that right now pushing on you is about 14 pounds per square inch. That means on your eyeballs right now, 14 pounds of air is pushing on them. Now, obviously, we can't really notice that because it's been like that your entire life, so you're used to it. Just like, how when you have on a really nice, soft sweater and you're like, oh, that feels so good on my arms, and then after like an hour, you don't even notice it? It's because your brain doesn't get signals to recognize things if it's used to it. Otherwise, your brain would just get completely overwhelmed. So that's what atmospheric is to our body. It's something that we've always had and we're used to, and so we don't even notice it. But there is air pushing on you. You feel the difference when you go on an airplane and your eardrums pop because there's less pressure that far above the earth. You also feel it when you go diving into the water, your eardrums pop now because you have the pressure of the water pushing on you, which is more than the pressure of the air when you are outside of the pool. Okay, so we're going to look at a few things about how volume varies with altitude. So remember, I just said that if you're flying in an airplane, your ears are going to pop because there's less air up here because there's less gravity. And because of that, your eardrums are going to pop because there's less atmospheric pressure. So we're going to notice the temperature, the pressure outside the balloon. The pressure outside the balloon is the atmosphere, or the air that you're touching and breathing right now. And then we have the pressure inside the balloon. Okay? All right, so let's see that again, hopefully without one of my pop-ups popping up in the middle of it. Sorry. And we notice that our temperature is dropping. So is the pressure outside. The pressure inside the balloon keeps bouncing up and down because the balloon is still inflated, so it needs to adjust for it. All right. Avogadro observed gases and their volume. Amedeo Avogadro was an Italian physicist who determined that the volume of a gas was related to the number of molecules in it. So how much space it takes up is related to how many molecules makes it up. Specifically, Avogadro proposed that at equal temperatures and pressure, equal volumes of gases will contain the same number of atoms or molecules. He reasons that in a volume of gas, the gas molecules were so far apart that most of the volume occupied by the gas was actually empty space. So it did not matter whether the gas molecules themselves were large or small. Although Avogadro's hypothesis was initially ignored, it was later confirmed by other scientists. So basically what that means is that 1 mole of oxygen takes up the same amount of space as 1 mole of helium. Takes up as much space as 1 mole of hydrogen. So it doesn't matter which gas it is, it takes up the same amount of space if you have a mole of it, as long as you're at the same temperature and pressure. What is the importance of Avogadro's hypothesis? It allows you to relate the volume of a sample of gas to the number of particles in that sample. Avogadro's work was important to developing the concept of the mole and later the ideal gas law. To consider gas volumes and moles, consider standardized temperature and pressure, or STP. The volume of a gas is influenced by temperature and pressure. Also, Avogadro's hypothesis states that at equal temperature and pressure, equal volumes of gases will contain the same number of atoms or molecules. While Avogadro's hypothesis relates the number of molecules or moles to the volume of a gas, Avogadro never specified a temperature or pressure. Chemists recognize the need to have some specified standard of temperature and pressure. That's because if somebody is doing an experiment on the top of Mount Everest, they're going to have very different results than if they're doing it on the beach in Jamaica, because you have different temperature and pressure. This standard was internationally agreed to be a temperature of 0 degrees Celsius, or 273 Kelvin, and a pressure of 1 atmosphere, 1 atm, or 100 kilopascals. These conditions of standard temperature and pressure are abbreviated as STP. 1 mole of gas occupies a volume of 22.4 liters at STP. Chemists found that when gases are at STP, 1 mole of any gas occupies a volume of 22.4 liters. This volume is called the molar volume of a gas. So the volume of a mole, molar volume. The implications are as follows. Dun, dun, dun. Number 1. 1 mole of any gas will occupy 22.4 liters. Number 2. This is only true at STP. Number 3. Molar volumes of different gases at STP contain the same number of molecules, and sub A equals, say it with me, 6.022 times 10 to the 23rd, regardless of the size of the molecule, Avogadro's hypothesis. So how big is 22.4 liters? A cubic box that is 0.28 meters on a side, about 11 inches, has a volume of 22.4 liters. Another way to envision a molar volume is that it is the space occupied by about 11 2-liter soda bottles, because that's something you're used to. So think about a 2-liter bottle of Mountain Dew. Delicious. And you have 11 of them. Wow. That's how big 22.4 liters is. A mole of gas at STP will occupy a volume approximately equal to 11 2-liter bottles of soda. So I did this recording a little bit different in that I read through all the slides and then we're going to go through our notes kind of as a review. So please hit pause and make sure that you have these notes written down and then hit unpause and we'll go through them. So these are our 6.05 notes and you have your keywords which are in the student guide. So molar volume, the volume occupied by 1 mole of a gas at STP, and remember this is 22.4 liters. So that's the volume of 1 mole. What is a mole? It's a collection of 6.022 times 10 to the 23rd particles, abbreviated MOL. Pressure is the force applied to a unit area of surface. I added atmospheric pressure. It's the force of the air around you pushing on you. It's about 14 pounds per square inch. That means there's about 14 pounds pushing on your eyeballs right now. There is less pressure as you go higher in altitude while your ears pop in an airplane. Why? Because you're farther from the center of the earth and there's less gravity. No, you don't need to know this last bit, but I think it is kind of important to know overall just because you're like, oh, that's why. Volume, the amount of space something takes up. For gases, it's measured in liters or milliliters. And so let's talk about gases. Number 1, a gas has no definite size or shape. It expands to fill its container. Number 2, as the temperature increases, a gas expands, and it shrinks as it gets colder. Number 3, Avogadro proposed that at equal temperature and pressure, equal volumes of gases will contain the same number of atoms or molecules. STP, standard temperature and pressure, is 0 degrees Celsius or 273 Kelvin. It's 1 atmosphere of pressure, so it's abbreviated 1 ATM, or 100 kilopascals or kPa. Main idea, when gases are at STP, when they're at 0 degrees Celsius, which is 32 degrees Fahrenheit, by the way. Let's add that on there. 32 degrees Fahrenheit. And there's 1 atmosphere pressure, so it's at sea level. Okay, so when it's freezing at sea level, it doesn't matter what gas it is. It doesn't matter if it's helium, oxygen, hydrogen, even though different gases weigh different amounts. At STP, 1 mole, or 6.022 times 10 to the 23rd atoms, of any gas will take up 22.4 liters of space. And it's kind of interesting because if we look back at our periodic table, hydrogen weighs 1. 1 mole of hydrogen weighs 1 gram. 1 mole of oxygen weighs 16 grams. It's 16 times heavier, but they take up the same amount of space. Because gas molecules push apart so much, there's a lot of empty space in between. So again, main idea, at STP, 1 mole of any gas will take up 22.4 liters of space. All right, so let's get to the math problems. How many liters does 2 moles of oxygen take up at STP? So again, start by writing down what you know, and you should be adding this to your notes. Put it over 1. What has to be on the bottom of my next fraction? Has to be moles. Why? So that my moles cancel. All right, so I want to go 1 mole. And what do I want my final unit to be? Well, I'm trying to find liters. Okay, so what's my equivalence of moles to liters for gases? So there are 22.4 liters in every mole. I multiply 2 times 22.4 and I simply get 44.8 liters is how much space oxygen will take up at STP. Okay, so let's work backwards. Let's say I have 112 liters and I want to know how many moles is that. Okay, so again, start out by writing down what we know. So we know 112 liters. We're putting it over 1. What has to go on the bottom of my next fraction? Liters, and I'm changing it to moles. 1 mole of any gas at STP is equal to how many liters? 22.4. In your calculator,